Okay, welcome everyone. So we're going to continue our discussion of Chern numbers and continue that to Chern-Simons gate theories today. So let me just quickly review what we talked about on Friday. We showed that every band structure has associated with it Berry curvature, which is simply the Berry curvature associated with the fact that the band structure can be viewed as a function of a parameter, which is the momentum, the block momentum. Okay, and then we showed that because the wave vector, the block wave vector, is defined on a torus, it's really a periodic function of momentum space. This implies that the integral of the Berry curvature over the entire Brillouin zone for any band is an integer, which is this famous Chern integer. Oh, sorry, I should be using this pointer here. Yeah. Okay, so every band is associated with a Chern number. This integer is called the Chern number. It's usually 0, but in cases where you have some sort of broken time reversal or inversion symmetry, these bands can have non-zero Chern number. And I think Hayu in tomorrow's section is going to look at a number of simple examples where you can compute the Chern number by some approximate methods. And strangely enough, since it's an integer, and if an approximate method gives you an integer, you're pretty sure you've got the right integer when in the regime where the approximate calculation is supposed to hold. Okay. All right. So any questions on that introduction? Yeah. Okay, we also talked about how Chern numbers can change. The only way they can change is by closing the band gap. And when you close the band gap in the simplest situation, you get a direct spectrum at the point where the bands touch. And this is something you'll see in the examples that Hayu works out tomorrow. And when you have for each direct node, what you find is that the Chern number of both bands change by 1 in a way that the sum doesn't change. So C equals 0 can go to 1 or -1, and C equals 1 can go to 0 or 2. Of course, the -1 case here corresponds to the 2 case over here. Okay, any questions? Okay, so what I want to establish today is this very fundamental relation, first obtained by Thouless et al., that the Hall conductivity of an insulator in 2 dimensions has a very simple expression. It's just E squared over H times the sum of the Chern numbers of the filled bands. Okay, so the way we compute this is to just apply the standard perturbation theory, which in this case is what's called the Kubo formula, which we've seen in I guess in some previous computations. So the Kubo formula, you apply vector potential, and the electric field then is the time component of the time derivative of the vector potential. And in the presence of the vector potential, you compute the current. So diagrammatically, the calculation is something like this. So here you have the electric field, which is vector potential of that you're applying to the system, and here you're measuring the current. And then you have to divide the full answer by omega, because the time derivative of the vector potential is the electric field. Now it turns out that the expression for the current and the coupling of the vector potential to the electrons are all both just given by the same quantity, which is the derivative of the Hamiltonian with respect to the momentum. So if you go back here, so here's our Hamiltonian with the vector potential in it, right here. So that's h of k, depends on k in some way. So dh dk is precisely the current operator. And dHdk is the same as dHdA because, well, K and A appear in exactly the same way. So therefore, you get exactly the same operator for the current as you get for the coupling to the external electric field. So the object that appears here, the vertex, is just the derivative of H is respect to K. Okay, so now you take the current operator with this expression and write it in the basis of the band block eigenstates. So the block eigenstates are labeled by a wave vector K and a band index, which I call M. So you have a band index M here and a band index M prime here. So this particular vertex will give you the matrix element between the band M and the band M prime. That's this thing that comes from that vertex. And this vertex here will give you this matrix element. Okay, or vice versa. Sorry, d by dkx is over here, and d by dky is over here. Okay, so that's what these vertices give you. Then how about the Green's functions for these propagators? Well, you just that's simply electrons with some dispersion. And you can just evaluate the frequency summation, and it gives you this very familiar expression that you get anytime you have a bubble diagram of electrons. It's the Fermi function at the two energies. EMK is the band energy, and then you get a plus I omega here because that's the frequency that you're inserting externally. And you have to divide the whole thing by I omega. All right, so now you have this expression. And what you want is the DC conductivity at zero frequency. So the first thing you should find is that this expression here, so let's put omega equals 0. Well, if you put omega equals 0 here, that's no problem because there's an energy difference over here. But putting it over 0 here leads to problems. So it must be that this expression, whatever it is, vanishes as omega goes to 0. Okay, it's a little tricky to show that there is no pole at omega goes to 0. But it turns out that this thing is indeed 0. And it requires, playing around with these matrix elements and seeing that they all add up to 0. And it relies on the fact that current is conserved. So I'm not going through the algebra here. In fact, I found something on the internet which goes through the proof of that, and I put that. Have I uploaded it? I think I have uploaded it onto the readings folder. If I haven't, I will upload it right after class. All right, so let's assume that the pole term disappears. So then what you have to do is to expand this to next order in omega. So if you expand this, then what you get is this expression here. So you're going to take 0 temperature. So this will tell you that this energy here has to be less than the Fermi energy. And when you have this term, the other M prime energy has to be less than the Fermi energy. And these two terms, after interchanging M and M prime, give you the following expression here. So this is the vertex matrix element. This is the same matrix element with M and M prime interchanged. And the Fermi functions you can see give you exactly this constraint over here, that one has to be above the Fermi level and the other has to be below the Fermi level. And then the square of this in the Linhart function gives you the energy squared. Okay. Now it's possible to do this calculation without using the Kubo formula and without using diagrams. Just do perturbation theory of the Hall current in the presence of an electric field. That kind of calculation is worked out in the book by Gervin and Yang, if you want to look it up. And you get exactly this answer. And lo and behold, this expression here is exactly the expression for the Berry curvature. So if you go back to our general expression for the Berry curvature, for an arbitrary set of, for the bands, and there it is. There's the Berry curvature that we had before. And this, of course, is just a special case of the very general expression for Berry curvature that we had way back when here. And it has the same structure. The derivative of the Hamiltonian with respect to your parameters, matrix element between n prime, and n prime and n, anti-symmetrized divided by the energy difference squared, sum over n prime not equal to n. So magically, the Hall conductivity is just given by, then okay, you simplify this, and this gives you star meaning right here, this star. Okay, so that's quite a remarkable formula, that the Hall conductivity is just a topological invariant. It's just the sum of the Chern number of all the filled bands. Okay, so this is an expression evaluated for free electrons. And you might wonder, what do interactions do to this? The answer, of course, is perturbatively they don't do anything, because perturbatively you can't change an integer, so it just got to remain the same. But another way to say this more formally is to think about what does this do in terms of the response to an electromagnetic field. So we just computed the response to an electric field, and we found it just a Hall conductivity. And we went through an argument for the Landau levels earlier that you could rewrite the Hall conductivity of a Landau level in terms of a Chern-Simons term of the external electromagnetic field. So we couple your insulator to an external electromagnetic field, A mu. And the fact that there's a Hall conductivity means that the effective action for the electromagnetic field is given by this term, which is called the Chern-Simons term for the electromagnetic field. We saw this earlier. And the coefficient is the Hall conductivity. And now the coefficient of the Chern-Simons term for each band is just the Chern number of the band. So it's the same Chern, of course, appearing in both cases. So the Chern number of a band leads to the coefficient of the Chern-Simons term. Okay. And this coefficient, very generally, because just the response to an electromagnetic field is quantized, can't change. And therefore, when you put in interaction, this also tells that the Hall conductivity can't change, and therefore it just remains exactly quantized. So, okay, that's a very rough argument, but it's basically correct. Okay, so now we know very simply what to do anytime you have an electromagnetic field or a gauge field coupled to a band with a Chern number. It just means that when you integrate out the electrons in that band, when they're fully occupied, you get a Chern number. We get a Chern-Simons term whose coefficient is the Chern number of that band. So a very beautiful and general result we're going to use a lot in the next week or two. And also this shows then, when we had the anomaly inflow argument relating the Chern-Simons term to the edge states of the Landau levels, that argument can be applied here with no changes, essentially. So this means that actually edge states would also be present at the boundary of any band that has a non-zero Chern number. And the total number of edge states must equal the sum of the Chern numbers of the occupied bands. Okay, so yeah, so that's an important prediction. So now, experimentally, there are many situations in which you can have a Chern number. Not just when you apply a magnetic field, you can also have a Chern number if you have some broken, like a ferromagnetic moment. And that's in fact been observed in twisted bilayer graphene. People have seen what's called the quantum anomalous Hall effect. Anomalous meaning that there's no magnetic field applied. Even at zero magnetic field, because of the Chern number of a band, you have a quantized Hall conductivity. And also that must accompany at the edge of this sheet of graphene, there must be edge states. Although I don't believe those have been directly observed, at least not for twisted bilayer graphene. People have seen edge states for ordinary graphene, but that's in the presence of a magnetic field. So that's not quite the quantum anomalous Hall effect. It's just the quantum Hall effect, integer quantum Hall effect. Okay. So I think, yeah, so that's the end of this chapter pretty much.
I'm sorry, can I ask a question?
Yes, please.
So you said something about interacting electrons, right? Like this discussion, does it? I mean, I'm kind of confused because I know that in like fractional quantum Hall effect, you need to take into account interactions, electron-electron interactions, and we also see like fractional, like quantized values. So
so
trying to relate it to this like Chern-Simons action, how to see like fractional.
Well, this just says that if there is a regime of stability, that if you're in a regime where free electrons give you an integer quantum Hall effect, then weak interactions won't change the value of the integer. It will remain quantized. That doesn't mean there could be some other entirely different phase of matter where you get some other quantized value. So it's just a statement of adiabatic continuity. So if you're in a regime where you're smoothly connected to the zero interaction limit, then you will have an integer quantized Hall effect. There could be a quantum phase transition somewhere, and you suddenly go to a new phase with a different value. That's not ruled out. This is just a perturbative stability argument.
I see. Okay, thanks.
Okay.
Can I ask a quick question?
Yes, go ahead.
So I was wondering if this ever works in some sort of disordered system where you don't really have translational invariance and there isn't really any good definition of a band. Like, would it always have to be a system where the disorder can sort of be perturbatively connected back to some clean system with translational invariance?
It does work in disordered system, and there's a nice paper by Paulus, also from the early days on that. I'll try to put that on the website. So there, the way you think about it is you take your disordered system, and then your parameters are the boundary conditions on your disordered system. So you have a strip or something, and then you have a boundary condition with a wave function changes by an angle theta between one edge and the other. And that's quite analogous to what happens in momentum space because of the block wave vector. I mean, the block wave vector essentially amounts to a twisted boundary condition in the Brillouin zone across the unit cell. Sorry. Yeah. So this wave vector tells you that the wave function has some twist which is related to k when r goes from 0 to a, where a is the lattice spacing. So the way you think about this, you think of your disordered system as the unit cell of a very large unit cell of an even bigger crystal. So say you have 100 atoms, all random. Then you just take your disordered system, those 100 atoms, and periodically reproduce them. But then you get a huge crystal where you can think of it two ways. You can think of it as a wave vector k in this big crystal, or you can think of a twisted boundary condition across the 100 atoms. So then your two parameters become the twist in the angle of the wave function, theta x and theta y, which is completely analogous to kx and ky across the system. So then you can argue that at least the average over boundary conditions of the Hall conductance should be quantized. So that pretty much is proven by what we have just proven. Mm-hmm. That if you have disordered system and you take twisted boundary condition, then the Hall conductance averaged over all possible twists is a quantized number. Then you have to make some argument that the twist doesn't change the boundary, doesn't change the Hall conductance. It has to be insensitive to the twist. So that's the non-rigorous part. That requires appealing to Anderson localization and all these other very subtle phenomena that are not rigorously established. But once you include all of that, then you have kind of a proof of quantization even in a disordered system.
I see. So it's quantized even for an individual realization, or is it only sort of quantized once you take an average over?
You can prove it's quantized once you take an average. Now, okay, for individual realization, you need some further argumentation.
Okay.
But it's insensitive to boundary conditions. And there are some numerical works on this who've tested that. In fact, that's true. You can just do it numerically and see that it doesn't. You do get the Chern number that you get by averaging over boundary conditions is precisely the value you get in any given sample because of Anderson localization.
I see. Thanks.
So,
may I ask a question?
Sure.
So here the Berry connection and Chern number are for isolated bands. So if we have
Correct.
degenerate bands, do we have a Berry connection as a matrix, and do we have associated Chern number of topological invariants?
Yes, I'm sure you do. I mean, there all these things have been studied. You can get then your Berry curve, instead of being like a U1 gauge field, become a SU2 or a U2 gauge field. And so it becomes more complicated. You get non-abelian Chern-Simons terms and so on. Yeah, you can. You have to have some symmetry reason to protect the degeneracy at all momentum for that to work. Yeah.
Okay, thanks.
Yeah, I think there is a lot of work on this. I'm not myself fully up on it, but yes, there are certain topological insulators where that's the case. Okay, we will get to some topological insulators and superconductors in a week or two. But yeah, great. Any other questions? Okay, so now we have developed some essential technology of what is Berry curvature and what's the Chern number, which is going to play a role in many of the things we're going to talk about from here. Our objective is to talk about, more complicated topological phases. We have met one anion topological phase, which is the Z2 spin liquid, and we have a reasonably complete understanding of it. We want to get to more complicated ones, like the fractional quantum Hall effect and non-abelian topological order. But before I start all of that, I thought the way I present things this year is to just take a field theoretical point of view and just talk about Chern-Simons gauge theories, just as gauge theories on their own right. In fact, this is how, it was written in a very famous paper. Just approach this as a mathematical problem. What is the definition of Chern-Simons gauge theory and what are some of its properties? This was, I think even before the idea of topological order existed in condensed matter. And eventually these theories that Witten was looking at turned out to be very relevant to topological phases, and that's what we're going. So we're going to kind of follow the historical order here. We'll just take Chern-Simons gauge theory as just some quantum system of some interest, and they turn out to be really, the first example, exhibit A of a system with what we now call topological order. Okay, so we're just going to quantize what are called Chern-Simons gauge theories. So, you've seen, presumably in some of your advanced quantum mechanics courses, how to quantize the electromagnetic field. You take the Maxwell action, and then you find your P's and Q's, and you convert the Poisson bracket between the P and Q's to the commutator, and therefore then you have a theory quantum theory of photons from Maxwell electrodynamics. So we're going to just do the same thing, except instead of taking the Maxwell action, we'll take an action which is one less derivative. So idea is we are talking about a U1 gauge field. In fact, this action here has n U1 gauge fields. So you have n U1 gauge fields. And we'll need more than one in several important cases, which are labeled by A sub I. So I goes from 1 through n, and mu is the usual space-time index. And then we want to take an action, which is the Chern-Simons term. And you can view the Chern-Simons term as the simplest action, which is consistent with gauge invariant up to boundary terms. But for now, let's just put the whole thing on a torus. So there's no boundary. We'll just take a compact space-time without a boundary. And then at least a compact space. And then this is the unique gauge invariant term I can write down with one derivative. It turns out to be also Lorentz invariant, but that's just a bonus. We only demand gauge invariance and we get Lorentz invariance automatically. In fact, this action is not only Lorentz invariant, it's conformally invariant. It's in fact even independent of the metric of spacetime. That's what makes it topological. But let's not worry about those subtle features for now. So then this action is then specified by this matrix. Kij is a set of numbers, which is often called the K matrix. And it has to be symmetric. You can just see by integrating by parts if you that this is so the K matrix of Ij matrix elements couples the ith gauge field to the jth K field. Okay, so that's the definition of the action of the Chern-Simons theory. So this is U1. People say this is U1 cross U1 cross U1 n times with a K matrix K. Sometimes if you just have one gauge field with a number K, then K is just a number. And then people say that's U1 Chern-Simons at level K. So level generally refers to this coefficient K. Now it turns out for this theory to be consistent, the K matrix has to have integer values, and we'll see that in a minute. Of course, you might say, well, why can't I just rescale the gauge field and make the K matrix have any values I want? So here the assumption in defining this Chern-Simons theory is that there are some particles around which carry integer charges of this gauge field. So if you have some particle which is moving around in space-time, it picks up an Aronoff-Bohm phase factor. And the assumption is that that particle is going to pick up a phase factor Q times A mu dx mu. So you have some path in space-time and the particle picks up this Aronoff-Bohm phase factor. So we are assuming here that there are some particles where this charge Q is 1. Okay. Now there could be Q could be 2 or 3 or 4, but we assume that there are only integer charges. And once you have the charge Q equals 1, then the normalization of A mu can't change. That's the normalization, so that the charges themselves are integers. Okay, so A mu are normalized so that, roughly speaking, when you do a gauge transformation, another way to say this, if you go A mu gets transformed to A mu minus d mu chi, then this chi lives on a circle of radius 1. So chi is completely equivalent to chi plus 2 pi, because the gauge transformation of the particles would be e to the I q chi, just by this Aronoff-Bohm phase factor. So the particles under a gauge transformation pick up a factor e to the I q chi. Q is 1, so e to the I, so chi and chi plus 2 pi are the same. So the assumption is that A mu is a U1 gauge field, meaning it really lives, its gauge transformations live on a circle. Chi is the object that lives on a circle. Okay. So then it turns out that if you want to preserve this property in a consistent way, where these are some quantum variables, when you do the quantum mechanics, and we'll see that in a minute, the k's also have to be integers. Okay, so this U1 cross U1 cross U1 Chern-Simons gauge theory is described by a symmetric matrix of integers. So now I have an infinite, given an infinite set of theories, you give me some k matrix K with integer matrix elements, and that, it turns out, could possibly describe some topological phase of matter, as you'll see. But for now, let's just try to understand, somebody just, or Witten gave us this action. It's a legitimate action with all the right properties for a quantum theory. So let's try to understand the quantum theory. Now, what we'll show is that the simplest topological anyon phase we have met, the Z2 spin liquid, is one special case of these Chern-Simons theories. Excuse me for a minute. Okay, I'll keep talking, but okay. Okay, and in fact, the Z2 spin liquid is the n equals 2 case, where this is the K matrix, amazingly. So it's a K matrix at 0, 2 to 0. This turns out to be the simplest Chern-Simons theory, which has time reversal symmetry. And it is, in fact, precisely the Z2 spin liquid, as we're going to show, if not this lecture, certainly by next lecture. Okay. Another very important case is when n is 1, that's the simplest case, and k is just an integer, m. And that describes the fractal quantum Hall state at filling fraction nu equals 1 over m. So if you had a system of bosons, which you can have in gold atoms, which form a fractal quantum Hall state, then m is an even integer. For fermions, it has to be an odd integer. Okay. So, and there are other values of k that we're going to meet, and but the case that we've already met turns out to be this particular K matrix. Okay. So now our task is to just take this action. This is a classical action with some Poisson brackets. We want to take this action as just some classical theory somebody gave us and quantize it. And it turns out, and that's what Witten shows remarkably, that you can quantize it exactly. You get a complete exact solution in all kinds of situations of this Chern-Simons gauge theory, even for the non-abelian gauge fields. So now, it's no surprise to us that Maxwell theory is easy to quantize. It's a harmonic theory. But if you take the non-abelian, like the SU3 Maxwell action, which is the SU3 Yang-Mills action, that's nonlinear. It's got all kinds of nonlinear terms, and nobody knows how to quantize it exactly. Has all kinds of rich phenomena, including confinement. But the Chern-Simons theory, even for non-abelian gauge theory, is exactly solvable. Well, it's quite complicated, and you have to read many very sophisticated mathematical papers, and there's connections to the Joul's polynomial and all of that. But the answer in principle, if you talk to a sophisticated mathematical physicist, can be obtained in a short time. So we're now going to consider non-abelian, at least for now. I think one of you is making a presentation on non-abelian case in the course presentation. I'll just talk about, in fact, the simplest case of n equals 1, U1 Chern-Simons theory. Okay. So it turns out the reason this is what we call a topological field theory and also solvable is that it's a very special field theory in which the number of degrees of freedom is very small. In fact, it's just finite. When you take an odd, like Maxwell theory, then you put Maxwell theory in a box, and you get a photon, set of photons, so you get a bunch of harmonic oscillators, and you get one harmonic oscillator for each wave vector k, and there's no upper bound on k. So even the simplest theory, field theory that we're accustomed to, gives you an infinite number of degrees of freedom. We just assumed always that when you're talking about a field theory, you're talking about a system with infinite number of degrees of freedom, infinite number of harmonic oscillators, one for each wave vector k. It turns out that's not the case here. There's only a finite number of degrees of freedom. And so everything can be reduced to just diagonalizing a few matrices, amazingly enough. Now, I should also add, since this is still a field theory that's well defined, but in general, of course, we think of this theory in any real application as the low energy limit of something. So in general, you would also have a Maxwell term here will be present. If you got terms with one derivative, then when you go to next order and whatever gradient expansion you're making, there will be terms with two derivatives, and the simplest term with two derivatives is the Maxwell action. And now the theory, once you add this term, certainly has an infinite number of degrees of freedom. But it turns out that almost all of those degrees of freedom are above some energy gap. So that's really the more precise statement. There's an energy gap in this theory. And above the energy gap, there's an infinite number of degrees of freedom. But below the energy gap, where this term basically scales to zero, it's irrelevant. Below the energy gap, there's only a finite set of degrees of freedom. And these are the topological degrees of freedom. These are the degeneracy on a torus that we learned for the Z2 spin liquid. So, so a Z2 spin liquid we learned had a four-fold degeneracy on a torus. So what we'll show is that this theory, Chern-Simons theory, with this K matrix, has 4 degrees of freedom. In other words, 2 qubits. Okay, and so on. So for any Chern-Simons theory, you can, there are topological field theories with a finite number of degrees of freedom, which can be all computed. Okay, so that's all a very beautiful subject and very well understood, certainly better than I understand it by other people. Okay, but I'm going to talk about the very simplest case. So we take a torus of size Lx and Ly. Okay, so then I said it's gauge invariant because there's no boundary. And we consider the case n equals 1 with k equals m, an integer. Okay, we'll just look at that case. All right, so we want to quantize this theory. It's fully gauge invariant, so we just let's pick a gauge where a tau is 0. Okay, but we can't just set a tau equals 0 and 1. It's just too quick. We have to first look at the equations of motion associated with any gauge field. Those are the analog of Maxwell's equations, and then choose a gauge once you have the Maxwell's equation. Okay, so we first vary the action with respect to a tau for just the n equals 1 theory, and then you'll just find the equation of motion of 0 flux. So this tells us that if you have some spatial sector, there's no flux through it, no magnetic field. Okay, so B is equal to 0. So that means, oh, well, there's nothing left. How can there possibly be any degree? There's no magnetic field. Everything else is pure gauge, and you're done. But no, there's still something interesting. There may not be any flux through the sample, but there can be flux through the holes of the torus. Okay, so this is the usual thing we have met before. So you have some torus here. And this is one of the holes of the torus, and there can be some flux phi through the whole of the torus, where there's empty space. Okay, this is where all the Chern-Simons theory is defined, and that flux is still non-trivial, and it's measured, this phi, if I take a line integral of A on this curve C, the flux phi is just the line integral of A dot dl along C. So that flux is our degree of freedom. Okay. So how do we get, so since all the variations of A in this region is just pure gauge, let's just pick a convenient gauge. And the only degree of freedom we have is the line integral of A around both of the cycles of the torus. So let's just pick our coordinates, our gauge, so that's the degree of freedom. So we just say AX, I can ignore all the spatial dependence on AX. It's just a constant, theta X over LX and theta Y over LY. So now my degrees of freedom, Lx and Ly, the size of the box, are theta X and theta Y. So I've pretty much reduced it to at least just two degrees of freedom now, theta X and theta Y. Okay, but so they could still be harmonic oscillators of theta and theta X, theta Y. That will still give me many levels of different energies in principle, but it's much even simpler than that. Okay, so now imagine that we make what's called a large gauge transformation, like this. So psi is something that as x goes from 0 to L, as x goes from 0 to L, or to L sub x, then zeta will go from 0 to 2 pi L. And that's okay, because only e to the I zeta is relevant. So this large gauge transformation is properly defined. Okay, so yeah, so it's permitted on the torus. Now, if you make this gauge transformation, you can see we've chosen all our factors cleverly, and that what happens is that under this gauge transformation, theta x goes to theta x minus 2 pi L. So this means that the value of theta lives on a circle. It's periodic variable with a circle of unit radius. And theta y also lives in a circle. So our degrees of freedom, this is confusing in a bit, our space is a torus, but our degrees of freedom are also a torus. It's just theta x, coordinates of a torus with of theta x and theta y. So those are the dynamical degrees of freedom that lives on a torus. Like if you have a particle moving on a torus, where the coordinates of the particle are also a torus. Okay, there's a spatial torus, and then there's the coordinates. The dynamical degree of freedom or the gauge fields are these two angles, theta x and theta y. Okay, so those are our degrees of freedom. And of course, these are these Wilson loop operators, which is E2. So we can take the exponential and we'd call these Wx and Wy. And these are clearly, exponential of I times line integral of A dot dx around the two cycles of the torus. So you have the torus, you can take this cycle or that cycle and just compute the line integral of Ax and Ay, and those are Wx and Wy. Okay, so now Wx and Wy then are just complex numbers, and they are completely gauge invariant, and they are in fact the only gauge invariant objects we can make. And these are our classical degrees of freedom. Okay, so now we have to quantize this thing. So to quantize this thing, we have to determine what are the Poisson brackets. So identify our P's and Q's. And then we convert the Poisson brackets to commutators. Okay, the simplest way to do that is to just take this gauge field here, this gauge field and this gauge field, and just put it into the action with the A tau equals 0, and compute, this action here. So the spatial integrals are trivial. Just give you a factor of Lx times Ly. That cancels the Lx and Ly cleverly chosen there. And when the dust settles, this is what you get. So the action for theta is I times m is an integer over 2 pi times theta y d theta x d tau. Okay. And I think at some point here, this whole thing will only make sense if m is an integer, because theta x goes to theta x plus 2 pi. If you do a large gauge transformation on this action, you'll find that it only makes sense if m is an integer. Okay, but now this is a very familiar looking action. This is the simplest action we ever found of just a free particle. Even without any kinetic energy, its mass is infinity. So that's the peak, the usual action is pq dot minus h. That's your usual Lagrangian. So this tells us that theta x and theta y have a Poisson bracket or a commutator. Theta x commutator theta y is I times 1 over this coefficient, which is right here. Okay, 2 pi I over m. So this tells us that, if you think of theta x as your coordinate, then the momentum is whatever is left over, which is m theta y over 2 pi. So this combination is like a p. This is like px. And theta x is just x. Okay, so then commutator of x and p is I h bar. Here h bar is 1. And that's how you get this relation. Okay, so there's our quantum mechanics. There we have these two variables, theta x and theta y, which obey this commutator. Our Hamiltonian is 0. There's no Hamiltonian. I just have these commutator theta x, theta y. And I just have to figure out what is the Hilbert space that can accommodate this commutator. What are set of states that can realize this commutation? Okay. Now the nice thing to notice is that the gauge invariant objects, because theta x periodic, you should really write this in terms of the gauge invariant objects. Everything else is pure gauge, are wx and wy. So here's our very important relation. So I have these matrices, wx and wy, which obey this relation. It's not quite a commutator. It just tells you that wx, wy is a phase factor, e to the 2 pi I m times wy, wx. Okay, so these operators act on some state, which is this set of Hilbert space of this Chern-Simons theory. And that Hilbert space, these operators are some matrices, must obey this relationship. Okay, so we want to find some matrices which obey this relationship. So that's a mathematical task. I just tell somebody, here there's some wx and wy are some matrices, and can you find examples of such matrices with this property? So, let's look at an example. The simplest example would be m equals 2. Then this will just become I. And then you have the relation that wx, wy is minus. This becomes minus 1, e to the minus I, minus wy, wx. Well, that's a problem I can solve. That just tells me these are Pauli matrices, x and y, sigma x and sigma y, which anti-commute. So that tells me that I have to have at least two states. The wx and wy have to be, in the simplest case, and it's assumed we're in the simplest case in this whole discussion, that I have to have two states. And the wx and wy are the Pauli matrices x and y that acts on these two states. Okay, so m equals 2, as we'll see later on, describes the fractional quantum Hall effect of bosons at half filling, mu equals 1/2. And this tells us that that fractional quantum Hall states of boson on a torus at nu equals 1/2 has a twofold degeneracy, because I can realize at least a twofold. Everything else will be kind of accidental. This is the required degeneracy on a torus. Okay, so what's the answer for general M? Well, okay, I already said that. For integer M, okay. So you can work it out, and the answer is m. And here are the explicit matrices. So you take the mth power of wi. So the mth power of wi will commute with wx. Just from this relation, if you take m powers, you can see that that works out. And it will also commute with any power of y, of course. And so it commutes with everything. So something that commutes with everything must just be the unit matrix. Okay. So this tells us that the mth power of wi is just the unit matrix. Okay. Now suppose I diagonalize wi. It has some eigenvalues lambda. And the eigenvalues of wi to the m is lambda to the m, and that must equal 1. So the eigenvalues of wi can only be these eigenvalues from L equals 0 to m minus 1. Because these are the only eigenvalues that obey that the mth power is 1, as it must be, because Wm y to the power m commutes with everything else. So the simplest case there are m eigenstates labeled by L, which have this eigenvalue for wi. Okay, so so that's now, is there wx that satisfies this relation? Well, you can see this is, from this you can see that wx is like a raising or lowering operator for the eigenstates of wi. So if you, let's say, for example, if I define the action of wx on L to be a raising operator, mod m. So basically you have a circle. The way to think about it, you have a circle again, and on the circle you have m states. 1, 2, 3, 4, all the way up to m. And on each point, the wi acting on any one of these states, is just a unit number, e to the 2 pi I L over m. And wx, there we go, is just a number that, takes you from one to the other, takes you around the circle. That's wx. So wx is like the clock operator, moves the clock forward, and wy is the operator that points to m points on the clock. And if you take these states and these operators, you can see that's the simplest solution to this relation. Okay, so what we've shown is that there must be a Hilbert space of m states for the U1 level m, and these states all have zero energy in the Chern-Simons action. There's the Hamiltonian is zero there, but there are these states on which you have these operators. Gauge invariant operators can move you around. They have different eigenvalues of different gauge invariant operators. Okay, and that's basically the whole story. So these are the the topological qubits here, or m bits, and these cycles of the Wilson line operators can either like clock forwarding operators, or they give you the eigenvalues of different directions of the clock. So basically what we've shown is that there's only an m-dimensional Hilbert space. It's finite. It's even less than a harmonic oscillator. A harmonic oscillator does have an infinite set of states. Here it's more like a Pauli matrix, which had only 2 states. Well, this is m. So it's a field theory with just a finite Hilbert space. Okay, and these is what really needed to realize all the commutation relation of the degrees of freedom of this topological field theory. Okay, so let me finish by showing you my claim that this K matrix, well, it's not the complete proof, but to start out, this K matrix has exactly the right ingredients for a Z2 gauge theory. So now you go through exactly the song and dance, but for that K matrix, exactly the same arguments. It's just a little bit more complicated. So now, excuse me, you have two Wilson lines, one for the gauge field number 1 and the other for gauge field number 2. And I'll call these W and V. And you can go through exactly the same arguments. And what you then find is that Wx anti-commutes with Vy and Wy anti-commutes with Vx. And all other combinations commute. That just comes from just looking at the Chern-Simons action, just in exactly the same way I just showed you for n equals 2, really. So what's my Hilbert space now? Well, I need a qubit here. I need two Pauli matrices, X and Y over here, and I need a second set of Pauli matrices here. So I have really two qubits, each of them with a two-dimensional Hilbert space. So the total number of states is 4. Okay, and that's exactly the property of a Z2 spin liquid. In fact, this notation Wx and Wy and Vx and Vy, let's just go back to Z2 gauge theory. That was exactly what I defined here with the same set of anti-commutation relations. And these were defined as products of the Pauli operators, sigma x and sigma z along the different directions. But these quantities obey exactly the same set of relations that we found in the Z2 spin liquid. And now we see that we should really think of them as two U1 gauge fields, A1 and A2, which then give you exactly the same realization. Okay, so now you know why we introduced all of this, because this is just exactly what you get from this very simple Chern-Simons gauge theory now, which we have exactly quantized with no approximations for this K matrix. Okay. And the degeneracy is 4. Now, in general, and this is a little more complicated to show, it's better shown by a path integral method than the method I just showed you, but I just stated without proof. If you just go through these arguments for a general K matrix, the degeneracy turns out to be the determinant equal to this result. It's the determinant of K. And if you want to do this for a non-abelian gauge theory or an abelian gauge theory on an arbitrary closed manifold, well, then that's we have to look up Witten's paper. He gave some, well, very hard to read for me, very dense set of results where in principle all of that is contained. I'm just showing you how to get the simplest case of it. I think one of you is going to show a bit more for the non-abelian case in the presentations. Okay, it's 4 o'clock, so I think I'll stop there. Any questions?
Hi, yeah, I have a question. What is the equivalent of the GI operators for this realization of the theory?
The GI operators?
From the Z2 spin liquid.
Oh, you mean the GI was a gauge transformation, right? Which commuted to the Hamiltonian. It was like a generator of a gauge transformation.
Yeah.
Yeah. So, I mean, here the gauge transformation would be some kind of, I don't know. Good question. Something that generates this. So, but that we do by just Wy itself. I think, yeah. So I think right.
So here there is no dynamics in the bulk, so you don't need any charge in the bulk.
Right. Yeah, I think that's correct. I mean, so the analog of the WX and these VX and WX and VY and WY are the analog, basically like the GIs, but integrated around the loop of the torus. There's nothing else. Everything
Right.
in the bulk we have put to infinite energy.
Right. Okay. Yeah. Got it.
So how do we show these anti-commutation relations here? Because when we discuss spin liquid, we kind of, we use these arguments of like plaquettes, etc., and like loops, crossing these contours, the CX and CY contours. So how do we show that here when we don't have this language?
Well, if you do exactly what so you take this theory with this K matrix, and then you go ahead and quantize it. So then you'll have two fields, theta 1 and theta 2. And S theta for this case, you can sort of guess. So you'll have S theta, without actually working it out, will be I times pi, I over pi, times theta 1 x times d theta 2 y over d tau plus x interchange with y. So basically, now you have two gauge fields, A1 mu and A2 mu. Then by exactly this argument, you will get 4 theta variables, which I'll call theta 1x, theta 2x, theta 1y, theta 2y. And then I write down the action. I just write them down in exactly the same way. And instead of getting this action, I will get this action. And notice it's off diagonal in the 1, 2 index. And that's related to the fact that that K matrix is off diagonal. It connects level 1 to level, gauge field 1 to gauge field 2. And there was a 2 there. That's why this prefactor is 2i over 2 pi. Okay, now you quantize this, and you get some commutation relation, and then you exponentiate it, and then you'll get this. Okay, so just doing exactly what I did today, but for this 2 by 2 gauge field, just turning the crank, I will get this relation, which I got by very different methods for the Z2 gauge theory.
Yes. Okay, so, I see it now. Thank you.
Yeah. Okay, there's also other ways where you can start with the Z2 gauge theory, and then you can embed it in a U1 gauge theory with charge to Higgs field, and then you can do a duality transformation, and then when the dust settles, you will get the same theory. Okay, I think towards the end of the course, I might show you that other route, which is the way I first realized this. But this is a much simpler way to see it. I think people in the field theory literature had realized this kind of stuff.
So as we increase n, I guess and change k to some degree, are these all these theories classified in some way, or do people just for example take some value of n, then take some some form of k, and they have some new interesting theory, and it's like a whole industry now? What happened there?
Yeah, well, the theory is as written down, and there's years of theory that's all. But now you can try to put some restrictions. You want to put a certain set of quasi-particles. You can say, okay, I haven't introduced quasi-particles yet, so I want to now introduce certain Wilson lines in the theory, which are these quasi-particles, and I say, what is the set of quasi-particles that are allowed to have a consistent theory? Then further, you can ask, what if I have certain symmetries? Restricted to certain symmetries, what are the things that are allowed? I think a lot of that is classified, at least for the U1 case, but in general, probably not. That would, I think I think Xiaogong Wen has some claim of classification of even non-abelian cases. So so there's some selection rules on quasi-particles, and then it all becomes something to equivalent to classifying unitary modular tensor categories, and now I'm really talking about words I know nothing about. Yeah, so I would say this theory, pure theory as written on its own, is completely well understood and makes sense. The question is, how and when can it be realized in an actual microscopic theory, under what conditions? That's a much more difficult question. Yeah. Okay, well, I know I owe you another problem set. I think I have one more problem set before. I know you should all be busy with your course presentation now, but I think I'm going to, hopefully not too long, one last problem set before the end of the term. And but I hope by now you're getting started on your course presentation. The list is up, and I think almost everybody has their titles. It all looks very exciting. And one of us will be contacting you soon about scheduling a date, and I'm not quite sure how it's all going to work. But there's going to be several sessions of Zoom when you'll have a chance to present your sometime in December. Yeah. Okay, see you on Wednesday.
Thank you.
Okay.